Hello, everyone. Welcome back to our course on algebra. Today, we're going to talk about the alternating group, which is a subgroup of Sn, of the symmetric group. So remember that we have defined Sn, and Sn for a fixed n bigger than 1. Sn are bijections from x to x, bijections where x is the set on n letters, so just say a set on n elements, 1 through n. And we have been talking about these group and these bijections. So, for example, we proved at the end of the last um, video, we proved that every one of these elements, the elements are called permutations, that every permutation is actually a product of disjoint cycles. So here is 1f. So here I'm going to take n to be 6, and here is an f from x to x. We've denoted in several ways. The long notation is to tell you exactly where 1, 2, 3, 4, 5, and 6 go. So 1 goes to, let's say, 3, 2, 1, 5, 6, and 4. So that tells me where every one of the numbers go, and that defines a bijection from x to x. In short notation, what we do to write in compact cycle notation, we write it in the following way, which, as a matter of fact, is going to help me to directly write it as a product of disjoint cycles, which is how the proof actually went. So I'm going to start with 1 and then see what is the cycle of 1. 1 through the map is going to go, 1 goes to 3, and then 3 goes to 1. So 1 goes to 3, and 3 goes to 1, so that is one cycle. The cycle of 1 just goes to 1 to 3, and 3 back to 1, and that's it. Then what happens to 2? 2 goes to itself. I'm going to write it like this, but we usually omit numbers that go to themselves. And then take the next number that is not in either one of those cycles. Take 4, and 4 goes to 5. 5 goes to 6, and 6 goes to 4. So that closes, and this is that permutation written as a product of disjoint cycles. Disjoint because the numbers that are in one cycle are just not touched by the other cycle. So that is a product of disjoint cycles. Okay, so now we're going to define a subgroup that is called the alternating group, which is like a subgroup of this group. This group is called the symmetric group, although many people just call it Sn. And inside the symmetric group, the elements are permutations. And today, what we're going to define is, inside this Sn, I'm going to define a subgroup that we call the alternating group, and we denote by An. So how do we define that? Let me build some theory first. The first thing is that I'm going to define a element is going to be called a transposition if it's a cycle of length 2. Transposition is any cycle sigma of Sn of length 2. In other words, so sigma is just something, just one cycle, one disjoint cycle of everything else, and it just goes, I is sent to j, where I is less but not equal to j, and less than n. Okay, so that is a transposition, and it turns out that every non-trivial permutation can be written as a product of transpositions. Every non-trivial permutation, so an element of Sn, can be written as a product of permutations, as a product of transpositions. How? Well, I'm actually just going to give you a formula for how to write as a product of transpositions a cycle. And since every permutation is a product of disjoint cycles, I can write any permutation as a product of transpositions. So it turns out that, look at this formula, A2 through AN. If I have a cycle like that, this is in the cycle notation, I can also write it as A1 AN, this transposition, times A1 AN minus 1 times A1 A3 times A1 A2. Let's see that this works. Let's see where A1 goes. So A1 goes to A2. Let me do it just with the laser so I don't write all over the place. A1, so starting from the right-hand side, where does A1 go, this number? A1 goes to A2, and then A2 is not touching the rest of them, so A1 goes to A2 as claimed. Where does A2 go? A2 goes to A1, and then in here, A1 goes to A3, and there is no more A3s, so A2 goes to A3. Where does A3 go? This doesn't touch A3. A3 goes to A1. In the next one, A1 will go to A4, so A3 goes to A4, and so on and so forth. So this is a valid decomposition as a product of transpositions of any cycle. And now, since every sigma in Sn is a product of disjoint cycles, then sigma is also a product of transpositions of elements of order 2. Okay, so let's see some examples of this. So for example, how about 1, 2, 3, 4, 5 in S5? By the formula that I just got, this is also 1, 5, 1, 4, 1, 2, and 1, 3. And we can check that that is the case, that 1 goes to 3. I think I messed up. I meant to write the cycle 1, 3, 2, 4, 5. Okay, now, yes, 1 goes to 3, and 3 is not touched by those. So I do get that 1 goes to 3. Let's see where 2 goes. 2 goes to 1, and 1 goes to 4. I'm sorry, where does 3 go? 3 goes to 1, and 1 goes to 2. So 3 goes to 1, and then 1 goes to 2. So 3 goes to 2. Where does 2 go? 2 goes to 1, and then 1 goes to 4. So 2 will go to 4. Where does 4 go? 4 goes to 1, and 1 goes to 5. So 4 goes to 5. Where does 5 go? 5 goes to 1, and it closes the cycle. So it works as a product of transpositions. What about, let me write the same, but now let's do it for a product of 2 cycles. So if I have 1, 2, 3, and 4, 5, 6, I can write each one first as a product of transposition. So 1, 3, 1, 2, and this is going to be 4, 6, 4, 5, and therefore this product is 1, 3, 1, 2, 4, 6, 4, 5, and now it's written as a product of transpositions. Notice that I'm not claiming it's a product of disjoint transpositions. It's just a product of transpositions. Finally, I'll mention that you can do that in many different ways. So for example, 1, 6, which is a transposition, is a product of transpositions, but I can also write 1, 6 as 2, 3, 1, 6, 2, 3, for example. That is an equality. And also as 3, 5, 1, 6, 1, 3, 1, 6, 1, 3, 3, 5, and 5, 6, it turns out that that is an equality. Also, I'm not going to check it here, but so there are several ways of writing one cycle as a product of transpositions. There is a way, but there are several ways. What matters, though, for our purposes, is that although there is very many different ways, this is one transposition. This is three transpositions. This is seven transpositions. And what's going to matter is that those are an odd number of transpositions. It turns out that if I can write it, which I can, as a product of transpositions, the number of transpositions I use is always the same parity. So if I am able to do it in one way, with one transposition, every other way will be an odd number of transpositions. Let me show you why that is true. First, let me write a lemma. I'm not going to prove this one. If you want, you can see it in Judson's book. There's a proof of this lemma. It's not that the proof is by Judson, but you can find it in Judson's book. So if the identity transposition, or the identity transposition, the identity permutation, if I can write it as a product, if I write it as a product of transpositions, where each tau I is a transposition, then R is an odd number, an even number, sorry. So if you write the identity as a product of transpositions, then the number of transpositions always has to be even. Notice, by the way, and let me just write a remark here, that I definitely can do that in many different ways. For example, the identity, I can just take any transposition and write it as a product of two transpositions, or if I take another different transposition, I can write it as a product of four transpositions, and so on. So definitely I can write it as a number, any number of transpositions, as a product of number of transpositions. As long as that number is even, I can do that. What the lemma says is that any such decomposition of the identity as a product of transposition have to involve an even number of transpositions. So now let me show you that a consequence of that is the following theorem. If sigma in Sn can be written as a product of an even number, respectively odd. Rewrite that. Respectively odd. If this element of Sn can be written as a product of an even number of transpositions, then every expression of sigma as a product of transpositions have an even number, an even, respectively odd number of transpositions. So let's see why that is true. Remember that we have this lemma that the identity can only be done with an even number of transpositions. So let's prove this. So here's the proof. So suppose that we have sigma, and I'm going to write it as sigma 1 through sigma m, with m even, and each one of those sigma i's a transposition. Okay, so suppose I can write it with an even number of transpositions, and suppose that I have another way of writing it as tau 1 through tau n, where these tau i's are also transpositions. So let's prove that n is also even. So note that I can compute the inverse of sigma, by the way, sigma 1 through sigma m inverse. Remember that the inverse is the product of the inverses, but in reverse order. So this is the inverse of m times the inverse of the first one. And therefore, the identity, I'm going to use the lemma, so I'm going to write the identity as a product of transpositions, is sigma times sigma inverse. I'm going to use the sigma inverse that I have here. So I have sigma times sigma m inverse times sigma 1 inverse. But notice that these are transpositions, so the inverse are themselves. So sigma I inverse, it's itself because they're transpositions. If I have ij, the inverse is ij again because ij times ij is the identity. So this is just sigma 1, it's sigma m sigma 1 because they're their own inverses. So this is just sigma m up to sigma 1. Those are m transpositions. And instead of sigma, I'm going to write this other form of sigma that I have taus, tau 2 up to tau n, and then sigma m up to sigma 1. But now, how many transpositions do I have? I have n transpositions and m transpositions. So this is an expression for the identity as a product of m plus n transpositions. And the lemma tells me that m plus n is even. And I knew that m is even, and therefore n is even also, which is what I wanted to prove. And similarly, if m is odd and m plus n is even, then that tells me that n is also odd, which is the other part. So that proves what I wanted to prove. Okay. Also note, let me also remark here that if I have some element and it has an even number, it has a product as an even number of transpositions, and I have some other element that it is also a product of transpositions and it is also an even number of transpositions, then sigma times tau will be sigma 1 through sigma n, tau 1 through tau m has an expression as n plus m, which is also even. It's an even number of transpositions. And therefore, this tells me that there is some closure under these operations of products as long as we have an even number of transpositions in both cases. So that tells me that I can define an. An is going to be a subset of Sn, is going to be sigmas in Sn, such that sigma can be written as an even number, as a product of an even number of transpositions, with sigma transposition and m even. So that is going to be this is what we call the alternating group. And what we're going to prove is that this is indeed a group. So let me prove that theorem. An under composition. After all, these are still permutations of 1 through n, of the letters 1 through n, is a subgroup of Sn. Okay, so let's prove that An is indeed a subgroup. Okay, so here's the proof that the alternating group, it is a group, and it is in fact a subgroup of Sn. So I'm going to use that lemma we had to prove that something is a subgroup. We need that it is non-empty and that every product G times H inverse is also in An. So let's start with non-empty. I'm actually going to prove that the identity. So note that the identity permutation, I can write Sn is always for some n bigger or equal to 2. So there's still at least 2 elements. So I can write it as a product of transpositions as 1, 2, 1, 2. It's a product of an even number of transpositions. And precisely those sigmas that are an even product of transpositions are the elements of An. So the identity is in An. So it is non-empty. Great. So we have a non-empty subset of Sn. And now I want to show you that it is closed under multiplication and inverses. So now let sigma be in An. Then sigma is, it has an expression as an even product of transpositions. So where m is even, and each one of the sigma i's is a transposition. And therefore, like in the previous proof, the inverse will be sigma m inverse times sigma 1 inverse. These are transpositions, so their inverses are themselves. And therefore, this is sigma m times sigma 1. It is also a product of m transpositions that is even, and therefore sigma inverse is also it also has an expression as an even number of transpositions. So it is also in An. So finally, now suppose, let sigma and tau be in An. Then what about sigma times tau inverse? These has an expression as an even product transpositions. These we just saw that because tau is in An, tau inverse is in An, so it has an even number of transpositions in some expression. And if I use those expressions, then I get a product that has it has an expression as an even number of transpositions. So it is also in An, and that actually, remember that is enough to prove that something is a subgroup. We needed non-empty, and we needed that every time 2 elements are in it, then the sigma tau inverse is also in it. So we've proved that An is indeed a subgroup of Sn. Let's see it. Let's see one of these alternating groups. So for example, the easiest Sn. So let's take S3. Remember, S3 has the identity, and then it has 1, 2, 2, 3, and 1, 3, and 1, 2, 3, and 1, 3, 2. Now, what is An? So how can I find A3? So notice that these are transpositions, but themselves already have an expression as an odd number of transpositions, as a product of an odd number of transpositions, namely 1 transposition. So this is an odd number of transpositions in one expression. So all the expressions have an odd number of transpositions. So these do not belong to A3. However, 1, 2, 3 is 1, 3, 1, 2. And 1, 2, 3, 2 is 1, 2, 1, 3. And these ones, good news, these are expressions with an even number of transpositions. So every such expression will have an even number of transpositions, and therefore those are in A3. So A3 is the identity 1, 2, 3, and 1, 3, 2. That's great. Let's see that this is a subgroup, is it? Well, let's see that what is the subgroup generated by 1, 2, 3? The subgroup generated by 1, 2, 3 would include the identity. It would include 1, 2, 3, and it would include things like 1, 2, 3 squared, which is 1, 2, 3, 1, 2, 3. What's 1, 2, 3, 1, 2, 3? 1 goes to 2 and 2 goes to 3, so 1 goes to 3. 3 goes to 1 and 1 goes to 2, so 3 goes to 2, and 2 goes to 3 and 3 goes to 1, so it closes the cycle, is 1, 3, 2. So 1, 3, 2 is also in this in the subgroup generated 1, 1, 2, 3. And let's see how much is 1, 2, 3 cubed. That would be 1, 2, 3 squared times 1, 2, 3. I know 1, 2, 3 squared is 1, 3, 2. So let's see how much is 1, 3, 2 times 1, 2, 3. 1 goes to 2, and 2 goes to 1, so 1 goes to 1. 2 goes to 3, 3 goes to 2, so 2 goes to 2, and 3 goes to 1, and 1 goes to 3, so 3 goes to 3. So it is the identity. So that is it. So the cycle ends, and we see that actually A3 in this case is cyclic, and it is generated by 1, 2, 3. And it is indeed a subgroup because it's a subgroup generated by one element. That is a subgroup. Very good. So now, note, by the way, let me write it as a warning, that if I take Bn to be the subset of elements in Sn such that sigma is a product of an odd number of transpositions, is a product of an odd number of transpositions, then such a thing cannot be a subgroup. It's not a subgroup of Sn because, well, if I have an element that has an odd number of transpositions and I multiply by another element that has a product of that has an expression as a product of an odd number of transpositions, the product will have an even number of transpositions as a product, and it will be outside of Bn. So it is not closed under multiplication. It's not closed under multiplication. So let me show you an example of that. Again, with S3, always try to find the simplest example you can find. 1, 2, and 2, 3 are in what we would call B3, but 1, 2 times 2, 3 is 1, 2, 3, which is in A3 and not in B3. So those that have an expression as an odd number of transpositions are not a subgroup. Is the ones with an expression as an even number of transpositions that are a subgroup. Let me in fact prove, though, that Bn, it has the same number of elements as An, but one is a subgroup and the other one is not. And thus, the size of An is n factorial divided by 2. So here's the proof. Let sigma be a fixed transposition in Sn, and let's define a map that goes from AN to BN, such that every tau in here is going to be sent to sigma tau. Then notice that this is well defined because tau has an expression. So tau is what we call even, implies that sigma tau is odd, meaning that there is an expression of tau with an even number of transpositions. If I multiply it by one more transposition, now all of a sudden the number of transpositions in this expression is odd, and that will be in Bn. Okay, so this is meaning that tau is in An, and that tells me that this is in Bn, and therefore the map is well defined. Is it injective? Yes, it is injective, because if I have that sigma tau is the same as sigma tau inverse, I can multiply, I can cancel in groups, I can multiply both sides on the left by sigma inverse and get that tau was equal to tau prime. Is it onto? Is it surjective? Well, give me any element of Bn, then sigma inverse gamma, which is sigma is a transposition, so it's sigma gamma. This has to be in An, because again, this is odd, so it has an expression as an odd number of transpositions. So this has to have an expression as an even number of transpositions, and therefore it's in An. Even. Okay? And therefore, if I send sigma gamma through lambda, I will get sigma sigma gamma, which is gamma, and therefore it is onto. Great. So it is a bijection. That's lambda is a bijection. And since these are finite sets, it tells me that the order, the number of elements in each set, is the same in both sets. And finally, notice that Sn is disjoint union of An and Bn, because every permutation either has an expression as an odd number of transpositions or an expression as an even number of transpositions. So I get that they're disjoint union. They have the same size, so the size of Sn must be twice the size of An, and therefore the size of An is the size of Sn divided by 2, and we know that is n factorial, so the size of An is n factorial divided by 2. Very good. So next time we'll talk about another different subgroup of the symmetric group, which is the dihedral groups.